Hello everybody, this is Dr. Christopher White, and in this lecture we are going to be looking at geologic time. Alright, let's get going. So, what are we going to be looking at in this lecture? Well, in past lectures we have of course looked at the principles of relative dating and how we can apply those principles to taking a sequence of rocks and essentially putting them into a chronological sequence. So we've used things like the principle of superposition, principle of cross-cutting relationships, principle of inclusions, etc. So what we're going to think about now is we're going to think about the larger geologic timescale, and we're also going to have a think about how we can use isotopes to allow us to produce a numerical age for layers of rock. Alright, so here's our geologic timescale. So obviously we have the Precambrian down here at the bottom, and of course I'm sure you remember the Precambrian is made up of the Hadean, the Archean and the Proterozoic. And of course then we have the eras of the Phanerozoic, we have the Paleozoic, Mesozoic and Cenozoic, and of course we're right up at the top here. So what's the point of the geologic timescale? Well, the point of the geologic timescale is to help us correlate rock units across very large distances using fossils. So if we look at our geologic timescale on the left, we can see that we have the eras, we have the periods, and then we have the numbers, the values essentially telling us the age of the boundaries. Now, these numbers aren't actually important. In geology, you can get away without having these numbers. So why is that? Well, the thing is the geologic timescale essentially is based on the first and last appearance of certain key fossils or certain very distinctive rock units. So each boundary that we can see is actually defined by the first or last appearance of certain key fossils or certain distinctive rock units. So the numbers that you see on the right hand side, you don't actually need them. So what's happened? Well, in geology, what we've done is we've taken all the rocks we can find and we've put them into an order. We've ordered them using relative dating. So we have, for instance, for the Phanerozoic, we have the early rocks of the Cambrian at one end, and we have, of course, present-day rocks at the other end. And we've put all the rocks in between into a sequence. Then what we've done is we've split up that sequence using the first or last appearance of certain key fossils, or the appearance of certain very distinctive rock units. So for instance, we've gone, okay, here's our sequence, we've gone, right, we're going to split up this piece, we're going to use a certain fossil, let's say we'll use its first appearance here to mark the start of that unit, and we'll use the last appearance of another fossil to mark the end of that unit. And then we say, et voila, this unit here we're going to call the Devonian. And that's the basic principle behind the geologic timescale. So of course this means that you don't need these numbers on the right hand side at all. So what you can do is you can be in the United Kingdom and you can say, right, this fossil marks the boundary between the Pennsylvanian and the Permian. Then you can go to, well, you can say, let's say the first appearance of that fossil, marks the boundary between the Pennsylvanian and the Permian. Then you can go to central Russia. Then you can look at the sequence of rocks there and you can see, right, no, that fossil isn't in this sequence of rocks. Then all of a sudden it appears. And because that fossil has appeared, you are now at the boundary between the Pennsylvanian and the Permian. So you're transitioning from the Pennsylvanian into the Permian. And so, as you can see, you don't need these numerical values on the right-hand side at all. So the numerical values are actually much more recent, so they're 20th century additions to the geologic timescale. So they're referred to as absolute ages, and they are essentially produced through isotopic analysis or isotopic data, which is of course used to produce what we refer to as a radiometric age. So at the boundaries that we have defined using the first or last appearance of certain key fossils or rock units, in some instances, we are lucky that there is a layer of rock which we can date. That layer of rock is normally an igneous layer, and it's normally volcanic, so a lava flow or a pyroclastic flow of some kind. And it just so happens to fall on the boundary, and so obviously we can take that rock, we can take it to a lab, and we can date it. And we're going to discuss towards the end of this lecture how we actually do that. Alright, so here's another, slightly more complex version of our geologic timescale. And once again, you can see though, you can see all of these eons, eras, periods, and epochs. So, we're going to discuss, how we do it. Well, the first thing was, if you remember, I said we had taken our sequences of rocks and essentially we split them up. And we split them up using the first or last appearance of certain key fossils or rock units. And initially, when we split up our bits of our units of rock, we defined what we refer to as a system. Okay, so at the beginning we had the Cambrian system, Ordovician system, Silurian system, Devonian system, Mississippian system, Pennsylvanian system, etc. By the way, interesting story about the Ordovician system, which I'll tell you if you ever decide to take historical geology. So each of these systems has a distinct population of fossils, and the boundaries will be defined by the first or last appearance of certain key fossils or rock units. Now, later on, these systems were turned into what we call the periods. Okay, so as you can see, we have our periods here. They go from the Cambrian all the way up to the Quaternary. Excuse me, please. So later on, we added numerical values to these boundaries as discussed. So the geologic timescale is, of course, made up of these eons, these eras, these periods, these epochs. And we can see that the largest units are, of course, the eons. So that's the Phanerozoic and the Precambrian. And then we have our eras, the Paleozoic, the Mesozoic, the Cenozoic. Then, of course, we split up those into the periods. And then we split up the periods into the epochs. So you can see, as we refine, we split geologic time into smaller and smaller units. So once more, the boundaries are based on major changes in the fossil record, or in some circumstances, the appearance of certain key rock units. So this is a pie chart showing you the breakdown of geologic time. And the first thing you're going to notice is this. The Hadean, the Archean, and the Proterozoic make up 88% of all geologic time on Earth. So the Precambrian makes up 88% of all geologic time. So you can see, obviously, that's quite a large chunk, isn't it? So, excuse me. The question that's obviously going to spring to mind is, well, why is this? Well, we've just discussed that we split up the geologic timescale based on the first or last appearance of certain key fossils. So, in order to split up the rock units, you need fossils, don't you? And fossils with hard bodies didn't appear until about 541 million years ago. That's the start of the Cambrian. So once we are past 541 million years, we can start splitting up the rock record using fossils because they're there. However, before 541 million years, most life was soft-bodied. That means when it dies, the soft body decomposes and you do not get a fossil. So, of course, that makes it nigh on impossible to split up any rock unit that's older than 541 million years. And so early geologists went and said, right, this rock unit doesn't contain any fossils, so therefore we are going to call it the Precambrian. And so what happened is you have this whole chunk of geologic time when life was either not present or soft-bodied, which is this huge swathe here, and then it's only right here at 541 million years where life starts to develop hard bodies. So we see shells and skeletons appearing. So once we have that, we can split up the geologic timescale easily. So this, the geologic timescale is split up this way purely because, at this point, these segments here, we did not have life, or life was soft-bodied. So obviously it does not appear in the rock record. It's only when we hit this 541 million year number where we start seeing hard-bodied organisms appearing with shells and skeletons, and then we can start to split up the geologic timescale. So this is why the geologic timescale looks the way it does. So, okay. So what about the major boundaries that we see? Well, obviously, as discussed, 541 million years down here, this is when we start seeing hard-bodied organisms appearing in the rock record. Remember, that means shells and skeletons. So what about the other parts of the geologic timescale? Well, you can read along here what they're all named after, and I'm not going to go into them right now. For instance, most of them are named after British tribes. So, and of course we have the Permian up here, which is named after a region of Russia. So the question is why is this? Well, it just so happens that the Paleozoic systems, later called periods, they were defined by British geologists. The Mesozoic, on the other hand, well, they are defined by continental European geologists, normally French or Swiss, and so they essentially are given names which relate to continental European factors or features. So the boundaries that we see here are defined by major changes in the fossil record. So why do we have the Paleozoic, the Mesozoic and the Cenozoic? Well, of course, this one's easy. The appearance of hard-bodied life. Now right here we have the Paleozoic-Mesozoic boundary, and this is the result of a very, very large mass extinction, even bigger than the extinction that followed the impact that destroyed the dinosaurs. So this is referred to as the Permian-Triassic mass extinction, also called the Permo-Trias extinction, and this one was huge. Life in the ocean was decimated. Life on the land was decimated. It was really bad. It's about as close as we've ever come to completely resetting life on Earth and just going back to the beginning and restarting with bacteria. That's how bad it was. It was awful. And so obviously in this rock record, what we're going to see is we're going to see a whole load of fossils that were present in the Permian, all of a sudden gone. Completely gone from the rock record. And then all of a sudden we have new fossils coming in. And so this very, very major change, this sudden loss of a very, very large quantity of fossils, means that what we have here is a major boundary. Okay, so things like the Pennsylvanian Permian boundary, they'll be defined by the loss of maybe a few fossils or the appearance of a few fossils. But the Permo-Trias or Paleozoic-Mesozoic boundary, that's defined by a serious change in the fossil record, a really, really big shift. And of course that's also seen up here with the Mesozoic-Cenozoic boundary, also referred to as the KT extinction. This is the one that did for the dinosaurs. And once again we have this impact, so we have a huge meteorite comes smashing into the Earth, causes huge destruction, and of course it causes very, very significant change to the global climate. Of course, certain animals like the dinosaurs and other very important, very common animals in the oceans like ammonites, they were not suited to this sudden change, and so that was it for them, unfortunately. So once again, we see this very, very sudden shift in the geologic record. The Cretaceous, full of dinosaurs. The Paleogene, no dinosaurs. We have this very, very obvious, very distinct, large, essentially extinction of lots and lots of organisms. So once again, we use this as one of these major boundaries. And so we define this as the boundary between the Mesozoic and the Cenozoic, which of course we refer to as the Cretaceous Tertiary boundary or the KT boundary. So minor boundaries, so between the periods, they're defined by the first and last appearance of certain key fossils, or just simply fossil or rock units. These major boundaries, the Paleozoic-Mesozoic boundary, the Mesozoic-Cenozoic boundary, and the Precambrian-Cambrian boundary, or Precambrian-Paleozoic boundary, should I say, they're defined by very, very significant changes in the fossil record. And that's why they are used to essentially break up the rock record into the eras. So here we go. These are the important dates. So the Precambrian, that essentially starts 4.56 billion years ago. And it goes all the way through to the start of the Paleozoic. Now, I've been saying 541. Some information will give you the date as 542 million years. So there's a little bit of flexibility in numerical ages sometimes in geology. The Paleozoic-Mesozoic boundary is set at 252 million years. And the Mesozoic-Cenozoic boundary is set at 66 million years. So what you'll notice is, compared to the Precambrian, which is an absolutely gargantuan amount of time, almost 4 billion, or over 4 billion years, the Paleozoic at 290 million years, sorry, should I say the difference between here and here? So the Paleozoic is 290 million years, and the Mesozoic is 186 million years. So what you'll notice is these are actually quite tiny compared to the 4 billion years of the Precambrian. Of course, I should say the Cenozoic is 66 million years. So these are very small units, and we've discussed why that is in the earlier slides. Okay, so let's have a very, very brief look at Earth history. Once again, if this is the kind of thing that interests you, historical geology is a course that you may wish to consider taking. Okay, so here is our geologic timescale, and you can see now this one is very nice because it's actually split up the geologic timescale, based into realistic sized units. So we can see that the Precambrian here is gargantuan, the Phanerozoic is by comparison quite small. So if we look at the geologic timescale here, what do we see? Well, we can see that each of the periods has certain key, fossils appearing or disappearing associated with it. So, for instance, the late Proterozoic is associated with the first appearance of soft-bodied organisms. So we begin to see fossils of certain soft-bodied organisms appearing. Examples would be things like the Ediacarian fauna of Australia start appearing. So as we move into the Cambrian, we start seeing the first fish and the first chordates. So the group Chordata is essentially the group that's going to give rise to the vertebrates, animals that have spines. So as we move into Ordovician, we see a diversification of the Metazoan families, and as we move into the Silurian, we see the appearance of the first vascular plants on land. So each of these periods has certain key fossils associated with it, the first vascular plant, of course, being an organism called Cooksonia. Now as we move into the Devonian, we start seeing very major changes. We see the first appearance of jawed fish. Now, the development of a jaw is a very, very important thing because it's a very useful thing to have. And of course, we also see the appearance of the first amphibians. Now, these amphibians are important because these amphibians are going to make it onto the land. And so, between the Devonian and the Carboniferous, what we're going to see is we're going to see amphibians begin to develop much chunkier, larger fins, and these chunky, larger fins are eventually going to start turning into legs. And so we see the amphibians essentially leave the water, they go onto land, and that takes us into the Permian. And in the Permian, we're going to see essentially, I do apologize, that takes us into the Carboniferous. In the Carboniferous, we're going to see the appearance of the first reptiles. And as we move in from the Carboniferous into the Permian, we're going to start seeing the diversification of the reptiles. And we're going to see the appearance of a group of reptiles called the Rhapsids. And they are eventually going to give rise to the mammals. So you can see we have this nice chain here, but we can see each one of these periods has very, very distinct things happening. So as you move into the Triassic, we're going to see things like the appearance of the first mammals. Now the mammals appear very, very late in the Triassic. And we're also going to see the first appearance of dinosaurs. So it's actually a little known fact that for the Mesozoic, the dinosaurs are very, very common in the Jurassic and Cretaceous. In the Triassic, dinosaurs are actually not that common. They don't make up much of the population of animals. So it takes them a while to get established and become the dominant land organism. So as we move into the Jurassic, obviously we see dinosaurs diversify and we start getting the huge long-necked dinosaurs, for instance, like the sauropods that we can see here. But we also get changes. We also see some dinosaurs begin to develop feathers. Now, the exact reason as to why some dinosaurs develop feathers, that's a little uncertain. But we then see these feathers, we then see these dinosaurs with feathers developing into the first birds. So, so we see the first birds appearing in the Jurassic. As we move into the Cretaceous, what do we see? Well, we see the first appearance of flowering vascular plants. The angiosperms make their appearance. Now, the angiosperms are very, very important because the angiosperms make about 90% of all plant life on the surface of the Earth. So, the angiosperms obviously became extremely successful. Also, in the Cretaceous, we're going to see the first appearance of the very, very, very early primates. And of course, right at the end of the Cretaceous, we get the extinction of the dinosaurs. As we move into the Cenozoic, so we're going to move into the Tertiary here, we're going to see the appearance of mammals and their diversification. interesting fact, right at the start of the tertiary, it's not actually the mammals that become super dominant. It's actually the birds that initially make a big move and start to become the dominant species on the land, but they are eventually outcompeted by the mammals and we begin to take over. And then finally, right at the top here, we have the Quaternary, and the Quaternary is marked by the evolution of humans, so essentially the genus Homo. So, as you can see, each one of these periods has distinct things about it that we can use to help define it. So it's the appearance or disappearance of these certain key fossils which are going to help us split up the rock record. So the numbers here on the side, they're not actually required. Okay, so the first thing is, well, how do we actually know the age of the Earth? So I just told you the Earth was 4.56 billion years old. So how do we know that? Well, the thing is 4.56 billion years ago, the Earth would have been essentially just a huge sphere of magma. So obviously, that means no rocks. If you don't have any rocks, well, that means you've got nothing to date. So that's a bit of a problem, isn't it? So how do we know the Earth is 4.56 billion years old? So what we need is a piece of material from which the Earth was constructed, but that material hasn't melted. So obviously we need meteorites. So a meteorite essentially is a portion of a body in the solar system, so let's say something like an asteroid, that didn't become large enough to ever be a planet. So essentially this is the material from which planets are constructed. So the Earth would be made up of literally tens, hundreds of thousands of meteorites. So the problem with the thing about a meteorite is obviously because it never made it to a large enough size where it started melting, it means what you have is you have a nice pristine sample of very early rock from the solar system. So it's the meteorites from which we get our dates. Now there's one particular type of meteorite which we love, and this is called a chondrite. So chondrites are the type of, then obviously the least altered group of meteorites, and one group in particular, the carbonaceous chondrites, are by far and away the least altered. So when we want to date meteorites, we really love getting our hands on chondrites because they are typically relatively unaltered and they're often, in our opinion, the earliest material from the solar system. So the most primitive meteorites, like the chondrites, consist of a mixture of dust, chondrules, so these are little spheres typically of normally just one mineral, and that represents a very small particle that has actually melted and then solidified, forming a sphere or a near spherical shape. And these chondrules are often made from silicate minerals. A good example would be the mineral olivine. And we have another thing in our very primitive meteorites. They're called calcium aluminum inclusions, or CAIs. And, well, you'll be shocked to hear these are essentially bodies within the meteorite that are made of calcium and aluminum, and a few other bits and bobs thrown in. So what we can do is we can date the meteorite as a whole, but we can also date parts of the meteorite. We can date the chondrules, and we can date these CAIs separately as well. And so what we find out is the CAIs are actually what give us essentially the value for the earliest material in the solar system. So that is set at 4.567 billion years old. So of course, as this is the initial starting material, it's taken as the starting material, it's taken as the starting point for the Earth. So think about it. If you're building a house, okay, you take it from the point when essentially the first brick is laid. That's when you start building the house, right? The CAIs represent that first brick in the construction of the Earth. So here is a picture of a meteorite, and you can see within this meteorite we have these spherical particles here. So those are the chondrules. We can see the chondrules, they're all over the place here, and those are made of silicate minerals. Okay, and we also have these rather more random metallic looking parts, and these are the CAIs. And then we have lots of other material in between. That's going to be a mixture of much finer material, so dust. And it's all put together to make these meteorites. In this case, this is going to be a chondrite. So when we date the meteorite as a whole, we get an age of 4.54 billion years. But of course, as we've discussed, the CAIs, that's the oldest material. They're actually older than the meteorite itself. So of course, as discussed, asteroid formation represents the earliest stages of planet formation. So, that's why we use them to date the earliest date, or the starting date, should I say, for the Earth. And the dates we get from CAIs and meteorites agree very, very nicely from the information we have from other planets and other bodies. So the moon dates to 4.4 to 4.5 billion years. So the moon was produced by material that was actually knocked off the Earth, kicked off the Earth, during one particular very, very large impact between the Earth and another body which was probably about the size of Mars, called Theia. So Theia and the Earth crash into each other. Now, luckily, it was an oblique crash. So that, obviously, if it had been a head-on crash, that would have obliterated the Earth and Theia. So that would have been game over for us. But luckily, it was an oblique hit. So that meant that when the hit occurred, it did serious damage to the Earth and Theia, but it didn't destroy both parties, and they fused together to form the Earth. Now, this also meant that a whole load of material got kicked off into space. And what this material did is it formed a ring around the Earth. So for a very short period of time, the Earth had a ring like Saturn. And this material that was around, this ring of material around the Earth eventually coalesced to form the moon. Now, this impact between the Earth and Theia occurred relatively early in the history of the solar system. And so it gives the moon a very, very early date, 4.4 to 4.5 billion years. And that's simply because once all this material came together to form the moon, well, that was pretty much it. The moon hasn't really changed since then. All that's happened since then is the moon has been hit by an absolute mass of meteorites and comets, producing all the craters that we can see. But the rocks of the moon, they haven't really changed. We can also look at the rocks from Mars. So we do have some meteorites from Mars. So they're produced when big asteroids crash into the surface of Mars, and it throws up pieces of rock that actually leave the surface of rock, go through the Martian atmosphere, and go into space. And occasionally some of those pieces of rock will actually make it to Earth. And we can measure those pieces of rock and we can date them, and they give a date of 4.5 billion years. And then we have the oldest zircons from Earth. So the oldest zircons, they are representing the first stages of minerals beginning to crystallize, or should I say silicate minerals, beginning to crystallize from this magma ocean. And so they give a date of 4.4 billion years. So the zircons, essentially, they've been dated using a process called uranium-lead dating. And we're going to come on to that later on because it's super important and super useful. Okay, this is a great part to stop. This is a great place, to stop part 1. So once again, get up, have a walk around, get a glass of water, a cup of tea, cup of coffee, get a snack, and then come back when you're ready for part 2.